Okay, so welcome back, everyone. I hope you have had a good short break, because now we're going to go to the next topic. But before doing that, I want to see if there's any questions, because I already saw there was one question that was being posted to the chat. And that's, of course, a very nice way of doing it, although it is sometimes a little bit difficult for me to see while I'm presenting if there are questions in the chat. So also, as I said before, feel free to unmute yourself and ask the question directly. I think we are with a relatively small group, so I think we should be able to handle that while we're doing it.
Yeah, sure.
Mm-hmm. Okay, so the
microphone as you like, please. Everyone can use microphone to unmute himself and to ask questions to the lecturer.
So the question that was already asked was, is the damping rate inversely proportional to the size of the oscillating cavity? So that is actually a very good question. So in this case, the damping rate of the harmonic oscillator that we talked about before, when we talked about, say, the picture over here, this gamma, this damping rate, that tells us how quickly the energy leaks out, is of course something that we want to have as small as possible. In other words, we want to have the quality factor as high as possible. And that is one of the big goals in nano optomechanics, to make this gamma as small as possible, to make the quality factor as high. And indeed, usually what we have is that when we have very large systems, it is relatively easy to make them of low dissipation. And that's because you can, in principle, with quite a bit of effort, but still with quite a bit of effort, make very nice single crystalline mechanical devices. And then, of course, there's hardly going to be any defects, and you can make very high quality factors when you do everything well. However, when you now make your resonator smaller and smaller, for example, I've shown you the nanomechanical devices, and in this case, these nanomechanical devices have a lot more surfaces, and in these surfaces, there are always defects. And those defects are then going to play a more important role, and the trend is therefore also that the quality factor decreases when you make your devices smaller. So that is definitely something that we see. However, this is really the quality factor, because also when you make your devices smaller, they typically tend to vibrate faster. So your omega 0 is going to be higher as well. So these defects on the surface and so on is one contribution. There are in general many different types of contributions to the damping rate. And again, if we would have the full lecture, I could tell you more about two-level systems, Alkiezer damping, thermoelastic damping, clamping losses, and also air damping. But I think in view of time, we will not go there. Okay, I hope that has answered the question. Before I proceed, any other questions from the audience at this point? Okay, I don't hear anything at the moment. So then let's move on to the second big part of this lecture that we are having today, namely about the quantum limits. And probably when we talk about quantum limits, we cannot avoid talking first about the Heisenberg uncertainty principle. So this is, of course, something that you know very well from your quantum mechanics course, and you can find it in any textbook that you have in general. However, we'll see later on that that may not be the perfect model to describe what's going on in optomechanics. So we'll also have these other two things that we're going to dive into later on. But let's focus again on giving a short recap of the Heisenberg uncertainty principle. And in this case, it is good to know that in quantum mechanics, there are typically two different kinds of uncertainties. So first of all is our ignorance. That is that we don't always know what the state or the wave function is that our system is in. For example, you can see here on the left the eigenstates of the harmonic oscillator. You can see there's all these levels. We already talked about the Brown state that we have all the way here at the bottom, but there's also all these higher states. In this case, if we now have a finite temperature, then there is going to be a probability that each of these states is occupied. And we don't know beforehand, without looking, which one it is. So that is our ignorance. We don't always know what the state or the wave function is. But still, even if we now measure it and ask ourselves what is the eigenstate in which we are, or we cool it down to very low temperatures so that we can be sure that we are in the ground state, then still, even if this state is known, then the outcome is still going to be probabilistic. So in this case, we already looked at the example when we are in the quantum ground state, then we know for sure this is the wave function, this is the energy. But then when you ask, well, what is the position of your mechanical resonator, then it can be anywhere along this, this wave function squared. Of course, there's a larger probability to find the resonator where the wave function squared is largest than somewhere in the tails, but still there is going to be uncertainty. That is, there is a probability to find different outcomes, even if you know what the state is. So it is exactly this one that is kind of the fundamental one, because the one in blue, not knowing the state or wave function, is basically coming from one ignorance. But the second one, that one is really fundamental to quantum mechanics. And now, if we review what we know about the Heisenberg uncertainty principle, then in this case, we know that if we have a strong measurement, then this measurement is going to project the quantum state that we have onto an eigenstate of the operator of the observable. For example, we start with this state psi that we have here, and then when we do a measurement, strong measurement, then in this case, we know that after the measurement, we have projected the quantum state onto a new wave function. And then the measured value, mu I, that you're going to get is the corresponding eigenvalue that you have. So in this case, mu is the operator of the observable. Think of this, for example, as the position that you're trying to measure for your optomechanical device. Then you are going to find a certain position, and you know that after that, there is going to be a new wave function that is very sharply peaked at that location where you found your mechanical device. And then there is this operator u, and then there's also the measurement outcome that you're going to get. And of course, you don't really know which one you're going to get, because there could be many different positions where you can find your mechanical device. So the probability to find a certain measurement outcome is actually given by the overlap between that eigenstate mu I and the original wave function that you started with. And that thing absolute squared gives you the probability of the outcome mu. So that is if you want to do a single measurement. If you want to do two measurements, say on two observables, eta and mu, then if these things commute, no problem. But if those two observables do not commute, then the eigenfunctions will be different. And it means that if you first do a strong measurement of observable eta, that's going to change the wave function into the state eta I, which one we don't know, of course, beforehand, but one of these states will be selected. And this is now not any longer an eigenstate of the second measurement, mu. And it makes the second measurement outcome uncertain. So of course, this sounds pretty abstract, so we can make this a little bit more concrete by considering a spin 1/2 particle. And since we're now getting near the end of the summer school, I hope that by now you know that the spin 1/2 particle can also be seen as a qubit. But still, we know that in this case, we can describe the spin 1/2 particle using these Pauli matrices for the spin in the x, y, and z direction. And there were all these commutation relations between them. So in this case, we see that these Sx, Xy, and Sz are not commuting. But we also know that these qubits or spin 1/2 particle can be very nicely represented by the so-called Bloch sphere, where we can put at different locations on the sphere the different eigenstates of the operators. And in this case, we have here on the North Pole the up state, on the South Pole the down state, and then the linear combinations of these. Those are the eigenstates of the x and sigma x and sigma y operators on the equator. And for convenience, we will either use this different notation instead of up and down and x and y and so on. So in this case, we use this z plus here at the North Pole, z minus at the South Pole, and then x and y plus over here. x and y minus over here. And that is something that we can also represent by two numbers that we can write in a column vector. So that sets the stage. Here we now have a block representation, and you can see now the spin 1/2 particle is in the Z plus state. The arrow is pointing in the North Pole, and that means that in this case we are in the up state or Z plus state, and that if we put it in a column vector is the 1, 0 state. And now what we can do is we can do a measurement and ask the spin, what is now the spin component in the Z direction. And in this case, there are two outcomes, namely we can find it in the positive Z or in the minus Z direction. But when we look at the probabilities, that is, we are going to find the components of the eigenstate Z plus and Z minus with the wave function that we have, absolute value of this thing squared, then you see that only the PZ direction is going to give us a probability of 1, and the Z minus is going to be a probability of 0. So in other words, when the spin is pointing up, you're always going to measure that it's pointing up. So that's of course not so surprising, and indeed you'll find your measurement is going to be the one pointing up. And after this measurement, you are going to have the same state as before. So that is if you do a trivial measurement, but now let's do a measurement in a different direction. So in this case, let's measure in the x direction. And now we can do the same calculation of the probabilities, and you find that now the probability to find it in the x plus direction, that is in this direction, or in the x minus direction, that is that one over here, is actually equal to each other. And now you have 50% to find in x plus and 50% in the x minus. And now suppose you do the experiment and find that it's in the x plus, so the one indicated in orange. So then when you have find this x plus, this positive x component, this positive measurement outcome, after that you are now in the state x plus. So now a new wave function is in the x direction, x plus, and this is the new wave function. And then when we do again a measurement in the x plus direction, well, then we are again in the eigenstate, so there is a 100% probability to again measure the same x plus and no probability to find the x minus. So that was exactly the same as we saw on the top row. And now if we do again a measurement in the z direction, then in this case, again, we have now this wave function that we start with, and we have these two eigenstates for the sigma z operator. Then you find 50% to be in the z plus and 50% to be in the z minus. And after this measurement, suppose that we find the z minus outcome, we are in this state over here. So the thing is that by doing these measurements in different directions on our spin 1/2 particle, that is on our qubit, then in this case, we actually have uncertainties, and actually we have also changed the wave function from the initial one to a different one by doing those measurements. So that is if you have just a single spin 1/2 particle. If you now have two of these that you combine, then of course the wave function is now described by the product of those two wave functions. And we can do measurements on the individual ones. For example, if you measure the first one in the x, maybe you get an outcome that looks like this. Of course, you can also have, by chance, find it in the x minus, but suppose we have something like this. So now the state after that would be like that. Then we can measure now z for particle 1. And then in this case, we have the two probabilities. And if we now try to measure the z components for particle 2, then in this case, you still find that it is an eigenstate of the sigma z2 operator, and you find with 100% probability in the upstate. And in this case, we see that these two measurements that we have been doing actually do commute. So in this case, there is no extra uncertainty in this one over here, whereas there was extra uncertainty in the case when we did the x and sigma z on the same particle as we saw before. So that kind of sets the stage. So this is something, as I said before, that you find in most quantum textbooks. And this also directly relates to the Heisenberg uncertainty principle. So we see it is related to commutations. And in this case, the Heisenberg uncertainty principle tells us that the uncertainty in one of the measurement outcomes times the uncertainty in the other measurement variable is larger or equal than the expectation of the commutation between the two operators divided by 2i, and then you have to take the absolute value of this thing squared. So that is in its most general form, two observables, but we of course know it much better when we think about position and momentum. And in this case, when we think about displacements of mechanical devices, we have the Heisenberg uncertainty principle that we can write as uncertainty in position times uncertainty in momentum has to be larger or equal than h bar over 2. And that's of course something that we can now use to understand these kind of measurements. So in this case, the idea is that originally the laser is turned off. We have a certain position of our mechanical device. We don't know what it is, but we try to measure that by doing a strong measurement. In other words, we certainly turn this laser on with a lot of power, and then we are going to see how much light is falling onto the detector. And from that, we can hopefully infer very nicely what the position of your mechanical resonator is doing. However, when we, of course, use a strong laser pulse at a certain instance in time, we put a lot of light in the cavity, it's going to bounce back and forth, imparting the momentum. So in this case, we'll see that if you do now a strong measurement of the position, that is going to kick the resonator, and that's going to change the momentum of this resonator. And not only that, when we change the momentum, then the change in momentum means that there will be a velocity of this mirror, and when you have a velocity that is uncertain, that will result in a change in the position. So the mirror is going to move a little bit later. It has a different position. What position is going to depend on where it was originally that we just measured, but also on the velocity that the mirror will get. And in this case, that is something that is now uncertain due to the uncertainty in the momentum. So in this case, we see that that is going to result in a change in the position later on. So now what we're going to do is we're going to do a little exercise. So in this case, we're going to fill in some numbers to see how large this effect is going to be. So in this case, we're going to think about this kind of experiment. We have in mind the Heisenberg uncertainty principle. And now we are assuming that we are doing a measurement where the outcome is uncertain by delta U is 1 picometer. And then the resonance frequency of this device is assumed to be 1 megahertz, and we have to answer the following questions. Well, how large is the minimum uncertainty in the momentum right after doing the measurement? The second question is, well, if the mass of this resonator is now 500 picogram, what is going to be the uncertainty in the velocity? And then, as we saw before, differences in velocity translate into uncertainty in the position later on. So how long does it take for this uncertainty in the velocity to become as large as the initial uncertainty that we had in the position? And is this then shorter or longer than the oscillation period? So those are things directly related to this uncertainty principle. But of course, what we also would like to know is, well, this uncertainty in the momentum is caused by the photons. So what is the photon momentum if we assume a wavelength for the photons of 50-50 nanometer, a wavelength that we use very often in our experiments? And then when we have that, the final question here, well, the one but final question is how many photons does the uncertainty in the momentum delta P that we calculated in question 1 correspond to? And then we also want to compare the uncertainty of 1 picometer that we had to the quantum zero-point motion that we see over here. So there are these 6 exercises, and I suggest that you now take a piece of paper and try to solve for yourself these 6 different questions to kind of get a feeling for the numbers that are involved. So in this case, I think we will have something like 10 minutes now that we can use to fill in the numbers, and after that we will discuss the outcomes and the answers to this question. So please give it a try and see what the different answers are for these 6 different questions. Okay, so I think it is now 10 minutes since we started with this exercise. So I hope you actually got very well on your way to these 6 different questions. But of course, if you say, well, I got stuck at number 4 or so, that is also not a problem. It's just to get a little bit of a feeling for the numbers. And I think now we will take a closer look at those numbers. So we have those 6 different questions, and then the answer to the questions are listed over here. So in this case, the very first question was to see what is the uncertainty in the momentum, and we can directly use the Heisenberg uncertainty principle. We have to fill in the numbers, in this case h bar and also delta u, and then when you do that, we get here the 5 × 10⁻23 kilogram meters per second. So that of course sounds like a very small number, but actually it is correspond to a lot of photons, as we'll see later on. Well, if we now have the change in the momentum or the uncertainty in the momentum, then if we want to calculate what velocity uncertainty that corresponds to, then we have to divide by the mass. And in this case, the mass was 500 picogram. And in this case, keep in mind that if you have picogram, that's 10⁻15 kilogram, not 10⁻12. So that is a mistake that a lot of people, including myself, at some point make. So I'm just warning you that you have to take 500 10⁻15 here. And when you do that, you get an uncertainty in the velocity of 1.1 10⁻10 meter per second. So now that we know the uncertainty in the velocity, we can also see how that kind of relates or changes into a change in the position. So here we have to write this thing down. You see how it grows now linearly with time. And that means that if you want to know when is this delta U that you get the same as we start with, that's the 1 picometer. When you have this uncertainty, you'll find that it takes about 10 milliseconds for the resonator to acquire a large an uncertainty as large as the one that we had from the measurement. And that, as you can see, is much, much larger than the period of a single oscillation. So those were the first questions. Then we asked, well, how much is the momentum of a single photon with a wavelength of 1550 nanometer? And then the momentum of a photon is given by Planck's constant divided by the wavelength. And in this case, when you plug in the numbers, you see it corresponds to 4 10⁻28 kilogram per meter second. And this was, of course, something that we already saw on the introductory slide. But in this case, you have also been able to calculate it by yourself. So we see that the uncertainty that we have in the momentum is actually corresponding to a lot of photons. So in this case, we can divide those two numbers and we can see that it corresponds to about 1.2 10⁵ photons. So about 100,000 photons. That is the uncertainty in the momentum corresponding to. In case you're wondering, is that then also the number of photons that we should send into the cavity? Well, it turns out that this is in principle only the fluctuating part. So if you want to know how much photons that would correspond to, then you have to realize that this is actually the square root of the number of photons. So you have to take the square of this number to find the total number here. But that was, of course, not the question. The question was calculate this number here. And then the final question was to calculate the 0-point motion. How large is this extent of the ground state wave function? And for that, you can use this equation over here. You know what the mass is. The mass is 500 picogram. You know what the frequency is. It's 2 pi times 1 megahertz. And when you plug all those numbers in, then you'll find that's about 4 femtometer. So pretty small, and actually a lot smaller than this uncertainty that we had here of 1 picometer. And actually, it turns out if you would do the math, but now take this 0-point motion as the uncertainty, then you'll find the time for this to hold will actually be, roughly speaking, equal to the period of the oscillations. Okay, so I think with this, we have kind of set the stage. So you see, even if you have only 1 picometer of uncertainty, you still see that that corresponds to a small delta P, but as delta P is actually something that corresponds to lots of photons. And you also see that still for this to grow, you take a lot of time, at least many oscillations before you reach a comparable uncertainty. Okay, so that was kind of the uncertainty principle. But in this case, we see that if you want to have something like this, you have to do a strong measurement where the laser is initially off. Then you suddenly turn it on with a very large power, and that results in a kick. And this kick that you give it contains photons, and this photons number is uncertain, and that is going to lead later on to uncertainty. But this is, of course, not something that we have in mind when we talk about this this kind of measurements. Typically, what we want to do here is do a much weaker but continuous measurement. So in this case, the laser is on the whole time, not so strong as this this instantaneous strong measurement would do, but then still we are kind of capturing the whole time what kind of light is falling onto this photodetector here, and then from that we infer the position as a function of time. So a completely different idea that we have compared to this quantum uncertainty principle, the Heisenberg uncertainty principle that you find in your quantum mechanics textbook. And there's now two different approaches, the so-called House-Caves approach and that of the standard quantum limit. And the first one that we're going to discuss now is the so-called House-Caves derivation. And in this case, we are going to assume a few things. They're going to be quite general. For example, we're going to assume that the information, that is the information on the position of the mechanical resonator, is carried by bosonic modes. And then we know that in this case, our resonator is something that connects to the quantum world or to at least very small signals. And then our measurement devices are things that are in the microscopic world. So we would like to have a very large signal. So in this case, we are going to view the detector as in not just this single photo receiver, but the entire optomechanical system as an amplifier, where we're going to have a bosonic mode going in, carrying the information, is amplified, and in this case, there's also a bosonic mode that's coming out. And in this case, we're going to assume, so that's another assumption, that this amplifier is linear and it's time independent. And now to connect a small signal to the large signal that we can measure, we are going to need a high gain G. So those are kind of the assumptions that we make, and you can see they are rather general in this case. So in this case, there are a few very general assumptions that we can make, and still that is going to allow us to calculate quantum limits on position detection. Namely, we're going to follow now the arguments used by House and Caves. Okay, so I'm going to switch screens. So in this case, we're going to explore this using the theory. So I have to quickly change the screens here. Oops. Okay. Okay, so in this case, we're going to look at the House-Caves derivation of the quantum limit to position detection. And as we said, we had a number of assumptions that we make, namely that the information is carried by bosonic modes, and those bosonic modes are assumed to be at a frequency omega that we have. And in case you're wondering, what do I mean with bosonic modes? Well, you can think of this as for example, light that is traveling through a waveguide on a chip, but also through an optical fiber, or when you send light through free space, that would also correspond to a bosonic mode. That's, of course, in the context of optomechanics, very important, but also you can think of this bosonic modes as microwave transmission, where you can use coaxial cables or coplanar waveguides. In all of these examples, your information, your mechanical position is carried by bosonic modes. And now, when we talk about bosonic modes, then in this case, the important things are the creation and annihilation operators. So in this case, for bosons, these are the creation or annihilation creation operator. That is an A with a hat to indicate that's an operator, and then we put a plus to create bosons, and then we have the same thing, but then without the plus, and that is the annihilation operators. And in case you think, well, that sounds kind of vaguely familiar, but I don't really recall. then think back about the quantum harmonic oscillator that you no doubt studied in your quantum mechanics course, where there were these operators that were raising and lowering the states of the harmonic oscillator. And then in this case, there were also so-called commutation relation. So in this case, for bosons, the commutation relation is that you have a dagger over here, which is going to be equal to 1. And in case you're wondering again, what was this commutation, this commutator again, what was the meaning of that? Then in this case, it's going to be the first operator that you have in the commutator times the second one that you have, and then minus, and then the same thing, but then with the order swapped. So that is what we have here. And in this case, we know that this thing here corresponds to the number operator. And in this case, we have that this is the number operator after we have first created a extra boson in our harmonic oscillator or our bosonic mode. So in this case, we see that this corresponds to these number operators, and that the order in which you apply these operators onto states matters. So that is what we see in this case. What I also am going to forget at some point is to write the heads on top of those A's and A daggers. So I'm not even going to try to put all of these on the A's and A daggers. So for now, I'll forget about these and I write the operators without the heads. Okay, so then as I said, what we want to do is we want to amplify the signal. So we are going to assume that we have one bosonic mode traveling through, I don't know, a waveguide, a coaxial cable, and in this case, there's the input waveguide. Then we are going to have the amplifier, which indicates with this triangle and the gain G. And in this case, there's also going to be an outgoing mode. So this would be the A out over here. And now we have, say, the linear gain of the amplifier, and that is indicated with G. And it means that if you ask what is now the ratio of the power at the output to that of the input, then we have the so-called power gain. And in this case, that is given by G squared. And what do I mean with power gain? Well, that means that the expectation value of the number of photons in the output mode is going to be equal, is going to be G squared times larger than that of the input one. So in this case, this would be the output number of photons that you have in your bosonic mode divided by the expectation value of the number that you have in the input mode. So this is the power gain that we have. Okay, so that sounds rather easy, right? So now we have an amplifier that takes an input bosonic mode to an output bosonic mode. So the easiest thing that we can now think of is simply use the output operator being equal to G times the input operator. But as you can see, I put a question mark here and also putting it in red. And that's of course for a good reason. And the reason is that now if we calculate what the output operator commutation relation is, so in this case, A out dagger, then from the definition we see that this is given by A out dagger minus A out dagger A out. And then with this attempt that we're using here, then in this case that would be, well, G A in dagger minus G A in dagger G A in. And what is that? Well, you can see that this is actually G squared times the commutation between A in and A in dagger. And in this case, we know if we send bosons in, then these A in and A in dagger satisfy what we have over here. So in this case, we see that this is equal to G squared times 1. In this case, what do we have? Well, we have that this is actually the commutation of the output, but that is also bosons, right? So in this case, we should also have that satisfied this, but that is not satisfied. So we see that this is not correct. So where did things go wrong? Well, of course, we have this nice picture over here of the amplifier. And when you think about electrical amplifiers, then you probably know that amplifiers add noise. So every amplifier has noise added to the output. And in this case, the assumption that we had before was not the correct one. So in this case, we need to add noise. So in other words, we have now the output operator is going to be equal to G times the input operator, but we also have to add noise over here. So this operator N is the added noise. And now when we again calculate this commutation relation for the output, then in this case we are going to have different terms. So now we have G A in plus N, G A in dagger plus N dagger, minus, and then here we have G A in dagger plus N dagger, and here G A in plus N. So that's now the commutator that we have. Again, we are going to find many different terms. Some of them are things that we already know, some of them are new. But when we work out all the different terms, we see we're going to get G squared, A in dagger. We are going to find G A in with N dagger. That is basically the term that is coming from this one, from this one and that one. So in this case, that is the term that we have here, and there are going to be two more from this this first product that we have. Namely, we're also going to have now G N A in dagger, and also the cross product of N and N dagger. So plus N dagger. So that's the first product that we have. And then we also have the second product. So we have now minus, and then G squared A in dagger A in minus. So in this case, keep in mind there's a minus from the commutator. G A in dagger N minus G N dagger A in plus, sorry, minus this thing over here. This is now what we have, and now you can see there are a lot of different terms. So in this case, we see that this first term with the G squared is actually nothing but A in dagger commutator of this thing. And then also the last term is going to be plus, in this case, N dagger. And then there are now these cross terms that contain both the input boson operator and the noise term. So in this case, we are now looking at noise coming from the amplifier, and then whatever we put into the amplifier. So in this case, we can now argue that all of these terms here are actually zero if the noise is independent of the input. So in this case, those cross terms that both contain A in and contain N are going to be zero when you calculate the expectation value. And that basically means that now we are done. So now we have calculated the output commutator to that of the input commutator and to that of the noise. So in this case, we now see that this is equal to G squared times 1 plus, and then N dagger. So we didn't know anything about that noise. And all of that has to be equal to 1, right? Because we have also at the output bosons. So in this case, we see that from this very general argument that the commutator of those noise operators actually has to be equal to 1 minus G squared. So we see that in this case, these noise operators are not corresponding to bosonic modes, unless of course G is equal to 0. but I can tell you G is equal to 0 would basically mean you have an amplifier and you are not connecting the input to that amplifier. No, you're just throwing away everything that comes at the input and just look at the output, which just contains noise. So G is equal to 0 is a very, very bad amplifier. So that's not what we want. No, we want to have very large G, as we said before. And in this case, when you have very large G, you see that this commutator is going to be, well, very large. Okay, so now from this very general argument that that there has to be noise at the output, we see that we have been able to calculate now this this commutation relation. But of course, that's not what we're interested in, right? So we don't want to know properties of these noise operators. We want to know what is coming out of our amplifier. So in this case, what we would like to know now is actually let's look at the output of the amplifier. So in this case, what we are now going to look at is the noise in the output operator. And in this case, we're looking at the variance. So now you have to be a little bit careful, because usually we tend to work with like displacement, momenta, so things that are always real observables. In this case, these are bosonic operators. They are complex numbers or complex operators. You have to be a bit careful. It turns out this is equal to the uncertainty or the variance in the real part plus that in the imaginary part. But then in the end, what you can do is you can relate that noise to whatever comes on the input. And it turns out that in this case, this is now given by the 1/2 the expectation value of A out dagger plus A out dagger A out. So that is the first term minus, and then the expectation value of A out and A out dagger. So from this you can see there is the kind of symmetrized sum of those two products of the two operators. There's the 1/2, and also you kind of subtract the expectation value of these things. So this hopefully makes sense, that if you calculate variances, you calculate expectation value of things squared, and you subtract from that the expectation value of that other thing squared. So in this case, I hope this definition makes sense. We don't have time to derive this over here. Okay, so now we have this expression for the noise in the output, but what is it? Because we have just calculated, so here it still is, what this output operator is. So now we can fill in all the different numbers, and then in the end, what we are going to find is that now when we plug this expression that we have for the output into the expression that we have now for the noise, then in this case, we're going to find that there are going to be many different terms. So we now see that we have the output. The output contains the input, but also the noise. We have products. So we're going to get terms that contain the input squared. We're going to have terms that contain the noise squared, and we're going to have cross terms. So if we now first focus on the input terms, then after a little bit of work, you'll find that this is equal to G squared, and then in this case, 1/2 A in dagger plus A in dagger A in, that's the first term, minus, in this case, A in expectation value, A in dagger expectation value, and that's the first term. Then there are going to be many cross terms. I'm not going to write it out, but there's also going to be another term, namely the cross product of all those n's that we have over here. So in this case, when we take those into account, do all the math, you'll find that in this case, this is given by 1/2 n plus n plus dagger minus n and n dagger. So those are the second term coming from the noise term. And just as we said before, when we looked at those cross terms, we said the noise is independent of whatever we put into our amplifier. So also all those cross terms here are going to be 0. So now you see that we are left with two terms, namely g squared times, oh, that looks a lot like the expression that we started with, right? So in this case, this is actually nothing but g squared times the variance or the noise in the input that we have. So in this case, you see that at the output, we have the amplified noise that we put at the input of the amplifier. And in this case, we also have a very similar expression, but now for the noise terms. So in this case, we also add to this the variance in the noise term. And that is in principle the best that we can do. But actually, the work that we did before by calculating the commutator is actually now very useful. Because in this case, we can put bounds on the noise in the noise, if you wish. So in this case, when we now calculate this term over here, then we can use Heisenberg's uncertainty principle. And that one was given by the commutator of the operators that we had over here. So this is the term that we have to calculate. And now you see we need to know what is the commutator between n and n dagger. And of course, without knowing anything about what kind of noise and how it appears at this amplifier, seems very daunting. But wait a second, we have just calculated that here. So in this case, you see that without knowing anything, just assuming that it's a linear amplifier and with bosonic modes, we were able to calculate what the commutator is of this noise process. So I think that is always really amazing, but it actually allows us now to calculate that this value over here is 1/2 times 1, absolute value of 1 minus g squared. That is what we have here. And this is now the noise added at the amplifier output. And now when we think about that amplifier picture again, it would be something that we are adding, say, at this point over here. But also we can now say, okay, it is added to the output, but we could also imagine it is kind of added to the input and then also amplified. So we can either use in amplifier language, when you look in electronics textbook, input referred noise or output referred noise. So we can now also act as if it just adds up to the input and is also amplified by the amplifier. In this case, we can also write now the input referred noise, which would be 1/g squared times delta n squared. And this has to be larger or equal than, well, in this case, 1/2 1/g squared minus 1. So this is what we have. And now we see that in this case, the amplifier always adds noise. Well, when I say always, does it always add noise? Well, only when g is not equal to 1. So we see that an amplifier with g is equal to 1 is not adding any noise, but also in this case, it is simply passing through the input directly to the output without amplifying it at all. So in this case, when we have g is equal to 1, it is a pretty lousy amplifier. So what we really want to know is how do we get from this very small signal from the quantum world to a very large signal that we can measure in our macroscopic world. So in other words, we are much more interested in the limit of g much larger than 1. And then in this case, you see that this added noise is actually going to go to 1/2. So in this case, you see we add half a quantum of noise to the input. And this is pretty much the House-Caves derivation. So in this case, maybe it's now a good time to see if there's any questions about what we have done here before I switch screen again. So feel free to unmute yourself or okay, no questions. So then I think it's time to go back to the PowerPoint presentation and then we see what the implications are of this House-Caves derivation that we have just done here from a mathematical point of view. Okay, so in this case, we look now at the House-Caves derivation over here, and in this case, we see that we could now see our detector as an amplifier, and this amplifier needed to have high gain to connect a very small signal coming from the quantum world to the large signals that we need in our microscopic world. And for that, we needed to have high gain. And we saw that a fundamental assumption is that information is carried by bosonic modes, meant that we had to satisfy commutation relation between operators. And we found that in this case, the noise at the output is the noise that is already present at the input, as we can see over here, plus, and then this term over here. That's the added noise by the amplifier, by the detector, if you wish. And in this case, you can see we can have that as output referred or as input referred noise, where in the limit of high gain, this number will be 1/2. So the important take-home message here is that in the limit of high gain, half a quantum of noise is added to the signal. In other words, we're adding exactly the same amount as would be carried by the zero-point motion of a mechanical resonator. However, this of course sounds great, but this is actually a very general argument. It does not provide much insight in the physical processes. And for that, if you want to get more insight into what's actually happening, we have to turn to a more easy to understand system. And that brings us to the second topic here, the so-called standard quantum limit. And we have now seen this picture many times where we have optomechanical signal system, and then at the end of the detector, when the resonator is moving back and forth, we'll have an oscillating signal as a function of time. However, when you try to do such an experiment, you'll see that such a measurement is always noisy. So it is not going to look like this, but maybe more like this. And in this case, there will be technical sources of noise. For example, your laser wavelength or power is fluctuating. You have to use electronics and amplifiers that are by themselves noisy. Maybe you do the experiment and actually your cell phone rings, and that will also be picked up by the detector. Or you have power lines nearby or tram lines, many more technical sources. And usually when you spend a lot of effort in the lab to try to optimize and shield and stabilize things, you can usually get rid of them. However, there's also more fundamental sources. And in this case, we have to talk about the photon shield noise, which is really the quantum nature of light. So we tend to think of light arriving on the photodetector as a continuous stream of photons arriving there, or a continuous stream of light, as if you have your tap and you pour water, you think it is a continuous stream of water here. But when you take a closer look at very short times, you see that the light arriving at the detector consists of single photons, so much more like these droplets that arrive one by one at your detector. So in this case, when we have such a detector, then we have to ask ourselves, well, how do these photons arrive? And if you use a laser as a source of photons, then the photons will arrive independently of each other. And we can ask ourselves the question, well, how many photons are going to be detected in a certain time interval, say 1 microsecond, to be a bit more concrete? Well, that answer is that depends on the average rate, and the process is actually a Poissonian process. So in this case, the number of photons that you're going to get is a stochastic number, and the outcome depends on the average number of photons that are arriving. So if on average you are going to measure 4 photons arriving in 1 microsecond at your detector, then there's also probability to have 3 or 5 or even 10. It is a smaller probability, than 4, but still there's a finite probability to measure 10. If on the other hand you have now an average number of 12, then you can see this distribution has become broader. This is the Poissonian distribution. And also it has moved to higher values, and the expectation value is in this case 4, and in this case 12. So the average rate at which photons arrive is going to be proportional to the laser power that you use. But you can see it is not just going to be the average value that you measure over and over again. No, there will be fluctuations. And the width of the Poissonian distribution tells us how much noise there is. And from this picture, you can already see that in the case where we have on average 4, the distribution is narrower than in the case where you have 12 photons arriving on average. And the width of the distribution is in this case proportional to the square root of the number of photons that are arriving. In other words, proportional to the square root of the laser power. So now what we can do is we can think back about our experiments and try to measure the motion of this mechanical resonator oscillating back and forth in time. And then when we would simulate what such a measurement could look like, it could look something like this. And I don't know if you see any mechanical motion in here. Well, I don't. I only see noise in this case. So what do? Well, we can tune the laser power. And keep in mind that we have just seen that the noise is proportional to the power, to the square root of the power. So in this case, maybe what we do is we reduce the laser power. So then we should reduce the noise. And indeed, now you can see this time trace here, which has lower variance. So indeed, by decreasing the laser power, we have decreased the noise. But also, in this case, we don't see any mechanical oscillations. And it turns out that, of course, we also have to see how this is transduced. And in this case, the signal is actually proportional to the laser power. That means that the signal to noise ratio is power to the power 1 divided by power to the power 1/2. So the signal to noise ratio is proportional to the power, to the square root of the power. In other words, by going to lower power, we're going the wrong way. We want to have a higher signal to noise ratio, so we should increase the power. And indeed, when we do that, you get a measurement like this. And now when you squint your eyes, you can already start to see these oscillations inside the noise that we have here. So it's barely visible. So if we increase the laser power now a little bit more, then you can see now we have these sinusoidal oscillations that we're looking for. And of course, on top of that, there will be the noise. So suppose now that this was a measurement for oscillation amplitude of 1 nanometer. Then if we have now a smaller amplitude, then of course, the amount of noise that we measure is the same, but now the signal is smaller, as you can see over here. And it turns out that these two cases have the same signal to noise ratio. So the bottom line is that the higher the laser power, the smaller displacement is that you can see. And we can now plot the smallest motion that we can see as a function of the laser power. And in this case, you see that this resolvable motion is going down with the laser power, and it goes down as the square root. And this is really something that becomes smaller when increasing the laser power. However, when we talk about resolution and high resolution, we think about that as being able to resolve small motions. It is always very confusing to talk about small and large values for resolution. So instead, here we use the word imprecision. So this basically tells us how imprecise our detector is. And when this imprecision is lower, that means we can resolve smaller motions. So that's of course great. Increase the laser power more and more, and you get smaller motions that you can resolve. And as you know from this analogy with droplets, is that also when droplets fall into a bucket or in a pond, they also impart these little things happening over here. And also photons, as we saw, exert random forces when they impact on the resonator. That's what we saw in the exercise. So if we increase the power too much, then actually the motion that we're trying to measure will actually be larger. So there will be more motion, not just the one that we're trying to measure, but additional motion coming from the random force of photons impacting on this resonator. And this is an example of something that we call in general backaction, which is the so-called influence of a detector on the object that you're trying to measure, in our case, the mechanical resonator. And it basically means that now the resolvable motion as a function of laser power also will grow when we have more photons in our optomechanical system. In other words, we also have this line here where the motion actually becomes larger with increasing laser power. And now when we combine these two things, we see that this measured motion coming out of your detector actually has a minimum. And this is what we call the standard quantum limit, or SQL for short. So I think now we are at a good point to have another little bit longer break, because we have covered a lot of ground. We have looked at quantum limits. We have done the exercise where we looked at the Heisenberg uncertainty principle. We have gone through the math and the operator algebra with the House-Case derivation, which was a very general argument. And now we have a more specific detector in mind, namely the cavity optomechanical system with the movable end mirror. And we have now seen for the first time the standard quantum limit over here. So before concluding this second part of the lecture, let me see if there's any questions that are with the audience. So if you have any questions, then please feel free to unmute yourself now and ask the question. Or alternatively, you could also put it in the chat. So any questions from the audience? This is really your chance to ask any question you can have. So don't be shy, speak up. Okay, if there's no questions, then I think we will end this session over here. And then I think looking at the program, we will then continue with the third part of the lecture at 2 o'clock. That is 1400 hours in local time. So then see you back in 1 hour, and have a good lunch break. And of course, it would also be great if you can use the lunch break to reflect a little bit on what you have learned, and maybe also have some questions to get started with when we start with the third part.
Okay, thank you very much, Menno. So let us come together at 2 o'clock